Hi, Mitch Winger back with another video on data analytics and machine learning. In this video, we'll discuss receiver operating curves and ROC graphs. Okay, let's get started. We've just reviewed profit curves, which are useful but come with a couple concerns. First, the profit curve can change drastically if the population distribution is different than we expected. That is, if our class priors are off. Second, as you might imagine, profit curves are very sensitive to the relative levels of costs and benefits we have placed in the different cells of our cost-benefit matrix. If we are very comfortable with our class priors and our cost-benefit estimates, profit curves can work pretty well. Unfortunately, in many of the domains we'll be looking into, these underlying assumptions are fairly fragile. Fraud detection in particular poses challenges. The amount of fraud may change from month to month, and the location or locations where fraud takes place may change as well. We may have different budgets and costs than expected for our campaign or our investigation, which will result in changes to our expected costs. How can we address this? Well, one way financial models address this is by evaluating results given various costs and benefits. We often use a best case, worst case, and most likely scenario approach to estimating our model's robustness to changes in our assumptions. We could take it even a step further and generate many different profit curves, taking into account the full range of potential class priors, candidate models, and decision costs. Of course, this results in an unwieldy volume of graphs that we then have to sort through. Not a really appealing option. There is, however, an approach that can display the entire set of performance capabilities for a model, or even many models, on a single graph. The receiver operating characteristics graph is a commonly used method for displaying this performance comparison. We often abbreviate receiver operating characteristics to ROC or ROC. ROC analysis was introduced way back in the 1950s. A ROC graph displays false positives on the x-axis against true positives on the y-axis. Let's take a look at one. Here we have a ROC graph with classifiers labeled A through E. Note that in this case we have 5 discrete classifiers, each of which only gives us a class label, not a ranking or any other type of score. By looking at the confusion matrix for each of these classifiers, we can calculate the true positive rate and the false positive rate to plot each classifier's point on the graph. We sometimes refer to the true positive rate as the hit rate and the false positive rate as the false alarm rate. Now you see the blue dashed line, that represents our baseline, which for an evenly distributed class is the equivalent of tossing a coin. The lower left-hand corner represents never predicting positive and therefore never sounding that false alarm. The upper right-hand corner represents always predicting positive, where we will have a large number of false alarms. Note that the rates apply to the actual class. False positives are all negative cases that we incorrectly predicted positive, while true positives are those positive cases that we correctly predict. As a result, we also have true negatives and false negatives. False negatives would be those positive cases we incorrectly predicted as negative. No matter where we are on that blue line, we'll predict half of the classes correctly and half incorrectly. Model E sits right on that baseline, meaning that its performance is no better than randomly guessing. If you happen to build a model that's in the lower right-hand portion of the graph, that is below the baseline, that model actually performs worse than random guessing. Points farther up and to the left of the ROC chart are obviously considered better. Therefore, our perfect model would have a point right at the 0, 1 coordinate. Of course, I would be suspicious of any model that is that perfect, but modeling techniques do continue to improve, so who knows? Classifiers closer to the y-axis, like Model A that you see there, are considered more conservative, as they typically make positive predictions only when they have strong evidence. This means they make few false positive errors, but may also mean that they miss more true positives as well. Classifiers farther to the right, like Model C, are considered more permissive or aggressive. They often predict the positive class with weaker evidence. Of course, this means that they often are subject to a high false positive rate as well. Many real-world scenarios that you'll run into have a low rate of positive cases, so we're frequently more interested in a model's performance over in the left-hand portion of our ROC graph. It's good to have a high true positive rate, but a high false positive rate comes with its own problems. Even a moderate false positive rate may be more than an organization is willing to handle. If we think about how many classifiers give us a rank or a score, well, we can use those classifiers and our knowledge of thresholds to create a complete set of points on our ROC graph for a single model. We can then connect these points with a smoothing line, which we then end up calling a curve. How we do this is, well, we just create a confusion matrix for many different thresholds or even all the possible thresholds, and then we plot the false positive, true positive rate onto the ROC graph. Here we can see what that looks like. Each of the points on this ROC graph corresponds to the classifier's performance at a given threshold. For each threshold, we can generate a confusion matrix, which gives us the point for that threshold. From there, we can connect the points into that line that represents our model's performance across all the thresholds. This line is actually a step function for our model, but when we have enough thresholds plotted onto the graph, it can appear relatively smooth. We can create a ROC for each separate model that we're considering and plot them against each other on the same graph. Now, of course, this is where the fun begins as we start to compare those different models against each other. The ROC graph gives us a couple key advantages over a profit curve. First, the ROC graph separates the model performance from the target class distribution. Second, the ROC graph separates the model performance from the costs and benefits. And as you might imagine, as any data science project progresses, the costs, the benefits, and maybe even the expected distribution of the target population may change. The model's curve on that ROC graph, however, won't change, even if changing project assumptions mean that we now start focusing on a different region of the ROC graph than we thought we would. Getting back to our ROC graph comparing different models, one of the most important summary statistics for a classifier is what we call the area under the ROC curve, which we abbreviate as AUC. As the name implies, this is a single value measure that tells us how much of the ROC graph is below the curve for a particular model. Because this is a 1-by-1 grid, our area will then be between 0 and 1. Although the ROC curve for a model is much more informative than the AUC by itself, well, AUC is still useful when you need a single number performance indicator. In situations where we have no idea what the class distribution is going to be, AUC also gives us a decent starting point for comparison of our different models. And for you stats whizzes, AUC is equivalent to the Mann-Whitney-Wilcoxon measure and also quite similar to the Gini coefficient. In each case, the measure represents the probability that we're going to rank a randomly chosen positive instance ahead of a randomly chosen negative instance. That's it for this discussion on ROC graphs. I hope you found it useful. As always, be sure to check out the other videos in this series.